All right, so before we start talking about alkyne chemistry, that is a carbon-carbon triple bond, I want to do a really quick review of alkene chemistry, which is one of the last topics we covered in Orgo 1. In general, these slew of reactions are all kind of defined as an electrophilic addition, where we have a double bond serving as a nucleophile. And it is kind of a start of an arrow, and it comes and attacks and adds two things to the kind of left and right location of the double bond. And depending on the reaction conditions, there's a bunch of different things that we can add. So in Moodle, I have this document here that's just a one-page summary of a lot of the reactions we learned in that kind of electrophilic kind of unit 8 section at the end of Orgo 1. And one thing that we're going to find in this unit with alkyne chemistry is we're going to do a lot of the same chemistry. We're going to see a lot of these similar types of reaction conditions and adding a lot of the same groups just to triple bonds rather than to double bonds. So as kind of a super quick refresher, one of our first types of reactions are reductions or hydrogenations. And this is when we use something like hydrogen gas on a metal catalyst, palladium, platinum, nickel, so on and so forth. You can do platinum on carbon, palladium on carbon. Each of these are going to be ways in which you can add H and H to both sides of your double bond. This does have syn addition, syn meaning they're added on the same side or have the same stereochemistry, although in this case there is no chiral centers or anything to show on this specific example. The very first example that we actually talked about in Orgo 1 with regards to electrophilic addition is a Markovnikov addition of a HBr. And this is where we actually introduced the idea of Markovnikov, that you're going to have the double bond come and remove the H first and add it, generating a carbocation on your starting material. And you're going to try to generate the most stable carbocation. So you're going to put that H on the less substituted side, so the more substituted side can carry your carbocation. Then you'll have that bromine come and attack, and that's going to add to the more substituted side. So in like this example here, it's going to be added to the right side because there's two methyl groups rather than one. Now, every once in a while, you might want to form a product that isn't a Markovnikov addition, and the kind of general go-to if you're trying to do something anti-Markovnikov is use peroxides. So if you use HBr and then add a peroxide, this becomes a radical reaction. And kind of long story short, rather than actually adding your hydrogen first, you actually end up adding a bromine first through a bromine radical. So your radical will actually be on the other side, and that kind of is the reason why you get anti-Markovnikov addition. You can also do something very similar by adding an OH rather than a Br. This is going to be a hydration reaction rather than a halogenation. I guess a hydrohalogenation on the first one. So the simplest way to do a hydration or add an OH to a double bond is simply using acid and water. You can even just use an aqueous acid, and that is nice and easy way to get your Markovnikov addition. Now, one issue with this is you do form a carbocation, so you are susceptible to rearrangement. So there are a variety of different types of reactions that you can use that will give you a product that doesn't have the ability to rearrange. And here we have the anti-addition using the alkoxy mercury component. So if you add water and then your mercury or your HgOAc, that's your acetate. If you use that, you actually don't have a carbocation, so you can't get any rearrangement. And then at the end, you'll use a sodium borhydride to get your the final reduction. So that also forms your Markovnikov, your Markovnikov product, but with anti-stereochemistry between your H and your OH. Here again, I'm not showing any specific stereochemistry. Now, if you want to put your OH in the opposite direction, which would we call our anti-Markovnikov or our less substituted side, the most common is a hydroboration oxidation, and that's going to be using typically a boron complex. Here I've given a specific example of BH3 complex to THF. Any boron complex will be able to go through and do this type of reaction. Key thing is you form this kind of like four-membered reactive intermediate that has a bromine and oxygen, and then your 2 carbons of your double bond. You will then use peroxide, which is your kind of nice hint that we're going to do anti-Markovnikov, and then have your OH come and be added and take out your boron. And those are kind of the 3 main ways in which we did hydration reactions. We can also do a full halogenation, which is going to be adding 2 halogens rather than the hydrohalogenation we showed earlier, which added an H and a Br. The most common one is just Br2. If you add Br2, you'll form your bromonium, which is that 3-membered reactive intermediate ring, and then the other bromine will come with a backside attack. You would get, for example, here I've just shown one of the enantiomers. You'd also get the other enantiomer as well. Now, it's important on this type of reaction to use an aprotic solvent, or a solvent that's not going to interact with your bromine. So these would be, and this is going to behave like a SN2 backside attack. So you want the same types of solvents you use in your SN2. If instead you use a protic solvent, any type of like alcohol, for example, or here we list water, what will happen is the bromine ion is unable to actually do its backside attack because it gets kind of like surrounded or stabilized by your protic solvent. So it's unable to come and do a backside attack, and instead you actually get water. This is known as formation of a halohydrin, and this will occur if you use a protic solvent. So you add a Br and an OH, and these also have your anti-addition opted stereochemistry. Now, in terms of addition, your Br is going to behave a lot more like a hydrogen. So we kind of call this Markovnikov, where if you kind of think of your halogen and hydrogen, they both start with H. They're kind of same there. So you'll put your bromine on your less substituted and your OH on your more substituted. We can also add multiple OHs, and these are going to be a variety of hydration reactions. One of the things you can do is you can form an epoxide, and we'll talk about epoxides in just a second. If you have an epoxide that's formed, you can open it up with acidic conditions. That's going to protonate at the oxygen, and then you'll have your water come and open up the same as it does in the previous example. That's going to give you an anti-addition. You can also use either your osmium or your KMNO4. Your osmium tetraoxide is really, really expensive, but it has really, really good yields, and is a syn addition of 2 diols, or I guess 1 diol, or 2 alcohols. Those are going to have the same side. This osmium is going to form this interesting ring system, so it's a same side addition. You can also use KMNO4. KMNO4 has very similar mechanisms and is significantly cheaper. However, you have to really control the conditions because it can run away and it can get really, really messy, and it typically gets pretty crud yields. And you can also get cleaving to happen, which is actually breaking that carbon-carbon double bond altogether. So if you do use KMNO4, you want to use really, really cold conditions, but it will get you the same product. We did mention that we can ring open epoxide under acidic conditions. So how do we make epoxides? 2 ways. The first is going to be using any peroxy acid. There's a bunch of different peroxy acids, but one example you definitely have heard is going to be the MCPBA. It's a peroxy acid that has some extra stuff to help stabilize it, and it's decently cheap, and you're able to use it to pretty robustly get an epoxide. Epoxides have to be syn additions because you can't have a 3-membered ring where they're away from each other. That doesn't work. The other way you can actually make an epoxide is if you form a halohydrin. If you had a double bond and you use, for example, Br2 in water, you'd form like our starting material, which is the halohydrin. And then under basic conditions, you can actually get an epoxide to form. That base will go through and it will deprotonate your OH, giving you an O-. And then that O- will come do a backside attack on the bromine, kicking out your bromine, giving you that 3-membered epoxide ring. I know that's fast, but this is all stuff that you've kind of heard, and my goal was to be under 10 minutes, which we're going to be right at, which is perfect. But these are kind of like the series of Orgo-1 reactions that you'll want to know as we kind of jump into our alkyne chemistry, because we're going to see a lot of these again. So let's go ahead and wrap up the video there, and then I'll see you next time when we start talking about some alkynes.